Hi, in this video we will study the continuity of functions at points. We will start with the definition, we'll go through examples and finish the video. So let me recall that while trying to find limit of a function as x approaches to point A, we only study the trend of the values of function around that point, not at that point. So in other words, we completely ignore the value of the function at that point itself. In other words, limit as x approaches to A ignores the value of the function at A. And indeed, we saw examples that the function may not be defined at A, but the limit may exist. And we will see more examples actually today. So, a priori, there is no reason that these two things, the limit of function as x approaches to A and the value of the function at A, has a relation. This relation comes in or is forced by the condition called continuity or being continuous at point A. So this is the definition. Let f be a function defined on an interval, open interval, containing A. Then we say f is continuous at that point if, well, we know that the limit, well, we can find it, the limit, and we can evaluate the function at that point. But if these two are equal, that's when we say that the function is continuous at that point A. So we force the value of the function to be equal to the value, to the limit of function as x approaches to A. That's when we say function is continuous. And one more terminology, if f is not continuous at A, we say it is discontinuous at A, or we say f has discontinuity at that point. So this is another terminology you better to learn at this stage, and then we will use it more and more. Okay, so this is nice. Now that we have these ones, let me just add one remark that when someone says that the limit is equal to f of A, indeed what we have in mind is three different things. So by the definition, checking if a function, if f is continuous at A or not, what we do is we check these three things. First, we check that f is defined at A. In other words, A is in domain of F. Or other way of saying is that, well, F of A makes sense. It has a value at A. So that's that's first thing. The second thing is that the limit of the function as x approaches to A exists. That's the second thing. And the third thing is that these two numbers, the value and the limit, are the same. So, and they are equal. So we have to check these. Function is defined, one. The value, the limit exists, and the value and the limit, they are the same thing. Okay, so let's do an example. The first example is an example of the by graph. So check the continuity of f at points 0, 1, 2, 3, and 4. This might be a little bit different, up to 5. Okay. Yes, okay, so let me see. I have the graph here. Yes, that's nice. Okay. So just look at the graph of the function f and then tell me, yes, where it is continuous or not. So we will go one by one and check what is going on here. So first, let us check it at x equal to 0. It means what? We have to check if f at 0 is defined. Is it defined? So for that, we have to go to the graph of the function. When I go to graph of the function, above x equal to 0, there is a hollow point. There's a white bullet point. It means that, no, the function is not defined at that. So that means that, well, right away from that, we conclude that not discontinuous at x equal to 0. How about at x equal to 1? Okay, so at x equal to 1, I go up on the graph and you see, well, yes, it is defined. So f at 1 is about 3/2, 1.5 almost, yeah, something like that. But how about the limit? A limit of function as x approaches to 1. Well, you see that as we approach to x, values of y get closer and closer to, you see, that point, which is 3.1. Actually, from both sides I have to get, and then you see that, well, yeah, it is, the limit exists and it is equal to the same number as a result. So this is that, and we know that, well, 3/2 is equal to 3/2. As a result, continues at x equal to 1. How about x equal to 2? At x equal to 2, well, the graph has a value. Yes, that's f at 2. You see that point there? It is 0. Yeah, it is defined. So that is the first condition. The second condition, as function x approaches to 1, the value of the function, you see, this is going to negative infinity. From this side goes plus infinity. Actually, we know that this is minus infinity and limit of f of x as x goes to 1 minus is plus infinity. Well, it is infinity. It doesn't matter if they are equal or not. If they are infinity, infinity means that the lim of f of x as x approaches to 1 does not exist. So the second step, we're done. We conclude that this continues at x equal to 2. The function was defined at 2. It was, the value was 0, but not given. Okay. The third condition, the fourth one, at x equal to 3. Well, at x equal to 3, value of the function, well, look for the solid bullet point. So here f at 3 is actually, yeah, it is 1. How about the limit? Limit of this function as x approaches to 1. Well, it seems that we have to study it in two ways. One from left, one from right. Oh, sorry, this is 3. Wow, I'm making this mistake here. It's at 2, those ones. This is at 3. We have to study at that same point. Yes. So as x approaches to 3 from the right, well, it means that, okay, we have to separate this thing and use the one-sided limit. So f of x, as x approaches to 3 from the right, well, this is what will happen. So this will go down, and this is getting closer to 1, yes? So this is 1. But when we approach to 3 from the left, this is what will happen to function. It's getting closer to -1. So right limit is 1, left limit is 1. They are not equal. That means that the lim f of x as x approaches to 3 does not exist. Well, as a result of that, well, the function is not continuous. So this continues at x equal to 3. Yeah, let me make a little bit space here for myself just to keep the graph handy. Okay, how about this one? At yeah, well, something fell off. Okay. How about the x equal to 4? Well, value of the function at 4 as you go up, well, yeah, it is about 1. So let me just say 1. F at 4 is 1. Define, and we have the value. How about the limit as x approaches to 4? Well, when we get closer to 4, you see that the graph is getting, the values of y getting closer to this value, which is 2 here. So the limit of the function exists, and it is equal to 2. But the value of the function and the limit as x approaches to 4 are not equal. So that means, again, f is discontinuous at x equal to 4. And for the last one, this is the one. So when we go approach to 5, the function gets closer to this value, whatever that value is. Let me write 3.8, for example. The value of the function is 3.5. The limit is 3.5. So the 5 is 3.8. Well, I wrote 3.8. And it is equal to limit of the function as x approaches to 5, which is 3.8. They are equal, so that means that f is continuous at x equal to 5. You see, this especially at 4 and 0, it shows why we choose the name discontinuous. So if you start tracing the graph at this point, we have to do this and come back. So we have to kind of stop, do something else. It is not a continuous. So for this one, as you go down like this, you have to stop, do a hop on that point and continue. Or for this one, when you get closer, well, you have to jump up here. And that's the meaning of discontinuity at a point. Okay, so this was for a graph. Again, the definition is saying that we have to check these three things. But we need to do more examples, and I have prepared actually more examples in this other page. Let me just go on this page and see what we have. Check the continuity of function f at the given point. So we have 4, maybe 5 cases, and we have to study on different points. Okay, let's start for the first one. First one, well, the function is x squared minus 3x plus 5. Well, first thing, value of the function, f at 2, it is defined. You just plug in. This is polynomial. Polynomial is defined everywhere. So 2 squared minus 3 times 2 plus 5. And that gives 9 minus 6, which is 3. Very nice. How about the limit? Limit of the function as x approaches to 2. Remember, when we deal with polynomials, limit is basically you just plug in the value, yes? So this tells me that, okay, this step is already telling me that the limit is equal to the value, and actually the result is showing itself. So limit of f of x as x approaches to 2 is equal to f of 2, and that means that f is continuous at x equal to 2. And well, the same argument will go for all polynomials. Actually, we will see that all polynomials and all rational functions are continuous on their domain. Wherever they are defined, especially for the rational functions, wherever they are defined, they are continuous at those points. Okay, so that's the first one. The second one is, okay, this guy here, this is rational function. Okay, and we are studying f at x equal to 1. Negative 1, okay. Negative 1. So I will start finding if the function is defined at 1, is function defined at x equal to negative 1. That's the first step. The second step is limit. The third step is checking if these two values are equal or not. Here, right away, you notice that negative 1 is a root of the denominator. And we know that the rational functions are not defined wherever makes the denominator is 0. So it means that negative 1 is not in the domain of f. It's not in the domain of f means that it is not defined. So f is not defined at x equal to negative 1. And, well, if it is not defined, that means that the function is not continuous. It fails the first step. Exactly, first step. Okay. What will happen for the second one? Okay, in the second one, you see that there is a squared here. Yes, there's a squared there. Yeah. Okay, that's exactly the same function actually. It's x squared plus 5x plus 4 over x squared minus 1. But we kind of repaired it, and at x equal to negative 1, we said, okay, let's just define, not using this formula, but let's just put the value there, 2. It means that while we already include the negative 1 in the domain of this function, and f at negative 1 is actually equal to 2. It is defined. That's the first thing to check. The second thing is finding the limit of the function at that point, x squared minus 1 as x approaches to negative 1. Well, here I plug in -1 upstairs. It will give me, well, first of all, -1 limit of x squared minus 1 as x goes to 1. This is fraction, quotient view. We start with that. But we see that the limit of the denominator is 0. The limit of denominator is 0 means that we cannot use quotient law. Means that what? We have to check the numerator. And what about the numerator? X squared plus 4x plus 5x plus x as x approaches to -1. This is -1 squared plus negative 5 times -1 plus 4. And you see that this is 0. Wow. Numerator is 0, denominator is 0, numerator is 0. So we are in 0 over 0 case. Remember what we do. We find the vanishing factor both in numerator and the denominator. Because there must be a vanishing factor. Otherwise, y should be 0 in the numerator and denominator. The numerator, the composition is the famous a squared minus b squared. In the numerator, what we need to find two numbers which add up to 5, and when you multiply, you get 4. So I can say that, okay, plus 1 and plus 4 are two things. By the way, remember that the vanishing factor here is x minus -1, which is x plus 1. Yeah. So here there is a x plus 1 here, x plus 1 there. We cancel those ones. And what we get, limit of x plus 4 over x minus 1 as x approaches to -1. Now the limit of the denominator is non-zero, and we can use the quotient law, and we'll just send the limit up there or limit down there. And this is basically direct substitution property. So it will be -1 plus 4, -1 minus 1. This will give us 3 over -2. So we found the limit. Limit also exists. That's the second condition. Now we have to study if the limit and the value are the same. So value of the function at 2 is at -1 is 2. Limit of the function as x approaches to -1 is equal to -3 over 2. These two are not equal. That means the function is not continuous at that point. The limit exists. The function was defined, but these two are not equal. Okay. Let's check this last one here. Again, f at 0 is defined by this. It is -1. Limit of absolute value of x over x as x approaches to 0. This is, remember, this was absolute value of x is piecewise defined, so we will go for the left and for the right. And well, this means what? This means that we have absolute value of if we approach to 0 from the right, we are using positive numbers, so it will be just x itself over x as x approaches to 0. These two cancel, we get limit of 1, and that is 1. So the right limit is 1, but when you approach to 0 from the left, absolute value will multiply another negative sign to get rid of that negative sign of the number, and then you cancel, you get limit of -1 as x approaches to 0, and that means that this is -1. Right limit exists, left limit exists, but these are not equal. That means that the limit itself as x approaches to 0 does not exist. The left limit exists, the right limit exists, but they're not equal. So that means that the limit itself does not exist. Or again, this failed, the second condition failed, and then that means that the function is not continuous at that point, 0. Okay, so that was the example. Now the last thing is that different types of what will be different types of the discontinuity. So those discontinuity. Okay, here. Well, the way this is categorized or different groups are defined is based on if the limit exists or not. So we will start with this fact. Does the limit exist? So limit as x approaches to a exist. Okay, or the limit as x approaches to a does not exist. Yes. Okay, if the limit exists and the function is discontinuous and function is discontinuous, means what? That implies that either the function is not defined at that point, so either function is not defined, or it is defined but the value is not equal to the limit. So f of a defined but the limit and the function value are not equal. So either that or that happened. So it means that, well, that's why we have discontinuity. This kind of discontinuity is called removable. The name for this kind, let me just call removable. The reason for this name is that, well, actually, let me just go back quickly to the graph. Look at these guys. The limit exists, but the value of the function is not equal to that. I can redefine the function by removing the value of the function and defining to be the value of the limit at that point. So it is just, this is a nice discontinuity. We can remove it. We can make the function continuous by a very small piece. Or look at this example that we have up here. This one. Yeah, the value of the function at -1 is 2, and value of the function at limit of the function as x approaches to -1 is -3/2. Well, I can, let me do it with red one. I can change the value of the function to be -3/2, and in that case the function, the new function, let me call f tilde, will be continuous. So I can remove the discontinuity by changing the value of the function or defining function at that point. So that's called removable. What happens, what else? Well, the next case will be the limit does not exist. But this can have different cases. For example, it can be left limit exist and right limit exist, but these are not equal. If the right limit exists and left limit exists and they are not equal, the function doesn't have limit. The limit is not defined. And while as a result, it's discontinuous at that point. This kind of discontinuities, again, let me just go back to the graph here. this is happening, for example, in this case. Left limit and right limit are not equal. As you can see in these cases, there is a jump happening. This is why we call these guys the kind of discontinuity is called jump. Well, another case would be that we have infinite limit. That's another case of the limit does not exist. Well, that's called again infinite discontinuities, and there are other cases, but we just two important ones are the removable ones, the one that limit exists, function is defined or not defined at that point, but the value of the function is not equal to the limit. That's removable. The other one is when the limit does not exist based on the fact that left and right limits are not safe. So there will be a jump happening. So that's so these are two different kinds that I like you to learn for this course. Okay, so we started with the definition, we did graph example, we did some examples like that, and then we studied the different types of discontinuities.